So here we go. Okay, so what we're going to be doing today is it's astronomy and cosmology, which is what we did last time, but there will be a significantly different, oops, here comes somebody else. Nancy, hold on.
Mama Frodo.
Wait, we got, so that's not Judith, that's Nancy.
Hello.
Hi. So where did I miss Nancy?
No, that's me.
No. I mean, where did Judith go? I thought
No.
she was.
No, I think I thought she said something. She didn't feel well, so she wasn't coming.
Oh, okay. Okay, great. So we had an internet outage, so I'm at Dunkin' Donuts. Okay, that's what you see behind me.
Oh, well,
Okay.
because I tried to go on and it wouldn't go, and I was like,
No,
oh,
I couldn't get on to do anything. But this appears to be working. So let's cross our fingers and see where it goes. So we're already recording. So what's going on here is we're doing what we did. This is subject 7, which is astronomy and cosmology. But it's going to be significantly different than what we did a year ago, simply because there's been a lot of things that I simply missed and have come together in I think, a constructive way. So you judge for yourself about how we're doing. So I'm going to start with what we did last time. So you'll see. Let's see. I think this is going to do it. Yeah, here we go. I'm going to put it into slideshow mode. Okay. So can everybody see this? Everything okay? Yeah.
center it a little
actually-
better, Bart.
Come again?
Center it a little bit. The very top is cut off. I think you need to maybe bring it down a little.
Okay, let me see how I can do that. Where did this bar come from?
Yeah, your perimeters are cut off.
Okay. Okay, let's see if we can live with this. I apologize. I've never seen this before. There's a frame around it, which is what it is. Maybe it's a new software feature from Zoom. No idea. Okay, so anyway.
Possibly, Bart, you can make the screen smaller. That might be a solution.
Yeah.
Let's see.
That would be fine.
Oh, that took it out of share screen mode.
Oh.
I think it did. No, it took it out of slideshow mode. Let's see if I do a smaller screen. Oh, that didn't. It's control minus shrinks the screen. That doesn't seem to work. Shift minus. That looks a little smaller.
Actually, you want to enlarge that back to where
Yeah.
it was.
Yeah.
It's back where it is.
Yeah, it's the same
Okay.
thing.
There was
So
It's-
actually, it was okay when you had it in the
Okay, so
the various pages were shown.
Bart, just below where you picked slideshow, you had a choice of slideshow settings. You might want to go there and see if there's something you could do.
okay, hold on. Let me go back into. Let me see. I'll go into share screen. And I'll go here. Oh, wait, no, now it's in slideshow.
Good. That's awesome.
That's it. You got it.
You fixed it.
Okay. Okay, so here we go. Okay. So let's see if I can do anything here. What we were doing last time was we were looking at what is physics trying to do, and ultimately in this session we're trying to do what's called cosmology, which is where in the world did the universe come from, and where is it going? And what goes with that is that it started with astronomy, which was driven by observations. And those observations have really only been since, say Galileo with telescopes. There are a lot of eyeball observations prior to that where people could identify planets and stars, and they could identify the precession of the axes of the North Pole as it moved around and so forth. But it's really only been in the last 100 years that astronomy has really come into its own, as we'll see. So that's what's really driving a lot of this, and the astronomers are still struggling to try and make sense out of it. So, some people put down that there's really no rational reason for any of this, or there might be one rational reason, and that's what we're trying to find. And that's what I'm going to argue for here is there's a suggestion that a lot of things are pointing to what the right path is. So keep that in mind. So a typical thing that happens here is there's a very nice survey on the last 100 years of cosmology by this guy Peebles, who's at Princeton University, and he's just taken a huge amount of observational data and tried to put together, what in the world is going on here, with everything, and what in the world is the story. The problem is that he kind of ended the book just as things got really, really interesting. And that's what we're going to cover this time around. But there's a lot of things. I'm going to go back and revisit this with a nice YouTube video that'll summarize what he was talking about. So we started in astronomy with the planets, and those are all observed. People could see these things with their eyes, and then they noticed these rotations and inclinations of the different planets, which led to things like eclipses of the sun and the moon and so forth. And eventually astronomers realized at the very bottom that outside this, what we call the solar system, there's a gigantic cloud of debris that never formed into planets called the Oort cloud. And that's what we're inside, dealing with everything here. So this is, astronomy. And the thing that we find in a lot of these different myths is there's a cosmic egg, or something that is the birth of everything. The world egg, the universe egg, the cosmic egg, that's what's driving everything. And so the point in this, it's a metaphor. Something's hatching into existence. Sometimes the egg is on the primordial waters of the earth, but the eggs are symbolizing the unification of these two different principles of the white and the yellow inside the egg, and this is what leads to what we call life. So that's the metaphor to keep in mind. Now, when we get to cosmology, it starts to get very interesting, as you can see in 1912, when Vesto Slipher, who I would argue has the world's greatest astronomer's name, Vesto Slipher, was at by the Grand Canyon. There's an observatory there where this guy Lowell was, who said he saw canals on Mars. So Slipher did a huge number of observations of what were called nebula, and he noticed that these nebula, he had like 24 of them in his list, that these nebula seemed to be very complicated. In fact, every one that he identified turned out to be a galaxy. He just didn't realize it. And what came with this was he could see that they seemed to be moving away. He could detect a shift in the spectrum of light, so that what is red shifted. So if it's shifted to the red, the wavelengths get longer, or equivalently, if it's moving away from you, the light waves get stretched out, they get longer, and therefore are called red shifted. So what happened was Edwin Hubble took this list of things that Vesto Slipher had come up with, and he went out and he observed all kinds of things from this. and concluded that these really were galaxies that were out there. He did it in a very clever way. He looked for a particular type of star that was called a C-feed variable. And this star had a known intensity. It would flare up, it would flare down, it would flare up, flare down. And if there were several of these that were a known distance away from the Earth, and that gave him what are called a standard to go measure when he looked at things that were far away that were doing the same thing. They're just attenuated. So he could look at how much the attenuation was, and that gave him a measure on how far away they were. And this, for example, led him to look at the Andromeda Nebula, which is now the Andromeda Galaxy, and he realized it was 1 million light years away. Today, we believe it's 2.5 million light years away, but that's just a factor of 2 or so. So Hubble was on the right track. But what came with this was Hubble ended up noticing that all of these things were moving away from us, so therefore they must have all started at a common point, some sort of singularity, and this led into this notion of what's called the Big Bang, which we'll come back to in a second. And the thing to take away from our discussion here is that the Big and Bang is neither one. It wasn't big because it was coming down and everything was compacted together. And there really wasn't any bang because there's no sound. There's no way to have air have any acoustic sound or anything. But it's space itself that is stretching out to take things away from us. And then it's space itself that's coming back in on itself. So that's the thing to keep in mind. It's very counterintuitive that space itself could be doing these things. So let's go to the next one. I think this is all I want to cover. Oh no, the net of this is that if you look at most things today, they'll claim that the universe is 13.8 billion years old. That is from when it first started expanding until we got to where we're at today. A key thing to keep in mind is when the expansion occurred, that there was a long period of time where there was nothing but, I'll just say, nuclei of atoms. So they were in a gigantic fireball, a gigantic nuclear fusion activity, and they gradually cooled down. And it appears that it took 380,000 years for them to cool down from the initial explosion that occurred, and at that point they were no longer fusing together, and we could actually have light occur. That is, before then we couldn't have any light because it was just this nuclear fireball, but now things cooled down enough that we could actually have light pass around through the space that it finally cooled enough for us to do something. This one astronomer, Fred Hoyle, hated this Big Bang. He felt that the universe was actually in a steady state and that matter simply was created from time to time, and that was how the universe worked. And so he decided to make fun of this by calling this the Big Bang, and was horrified that everybody loved the term and that he'd come up with it. So let's see. I think that the other thing to keep in mind here is that Einstein in 1915 had published his theory on general relativity, and what he had was a model of the universe, but it wasn't stable. If there was gravitational effects, and everything would collapse on it. So he needed something to drive things apart. So he added an extra term, and everybody, since then has realized this is probably what is the dark energy or whatever, which is the expansion of space itself. Let's see. There's nothing here I want to cover. So what I'm going to do at this point is get out of this, and I'm just going to go over to, there's a nice, oops, hold on a second. There's a nice YouTube video on this. And let me see if I can pull that up. Yeah, here it is. Okay. So this is going to be very much the conventional wisdom. This is how they think up to, I'll say 10 years ago, everything worked.
What is the nature of the universe? How's that for a question? For
Oops.
a long time, we humans had no idea what was going on in the universe. To help, we made up
Did you freeze, Bart?
stories to either help us explain what we saw or to make us feel better about what we use speculation and just so stories. You're starting to get a grasp on the biggest ideas there are. What is the nature of the universe? Let's find out. By the turn of the 20th century, scientists knew the Earth was old. Darwin's theory of evolution strongly implied the Earth was at least millions of years old, and Lord Kelvin, a hugely respected physicist and engineer, confirmed the Earth was ancient, given that it must have cooled from an initially molten state. That takes a while, at least a million years. How old exactly, no one knew. As for the universe itself, it logically must be as old or older than Earth. A popular model for the universe was that it was static. It is and always has been as we see it now, and in general hasn't changed. Stars may be born and they may die, but overall, things pretty much stayed in balance. The universe always existed, always will, always had galaxies in it, and so on. There are variations on this idea, but that's it in a nutshell, and it's what many astronomers believe. This is important. When we try to understand observations in astronomy, we fit them into a framework of understanding, things we think we already know. When something doesn't fit, it's a problem. Maybe the observation is wrong, or maybe we're misinterpreting it, or maybe the framework is wrong. That's a big step to undertake and needs proper contemplation and skepticism. Science is a tapestry, and when you yank at one thread, the whole thing may need reweaving. Sometimes, rarely, but sometimes, you have to yank that thread. The thread that got pulled in this picture was first uncovered in 1912. That was when astronomer Vesto Slipher, who has the uncontested coolest name for an astronomer ever, started taking spectra of the so-called spiral nebulae, hoping to get some insight on their characteristics. Remember, this was before we understood what galaxies actually were. It took him several years of observations, but by 1917, he had observed 25 of them, and he found something astonishing. When he examined their spectra, he saw that almost all of them were highly redshifted. In other words, it looked like most of these objects were rushing away from us at high speed, millions of kilometers per hour. What could that mean? At this point, two different lines of work began to converge. One was by a Belgian theoretical physicist named Georges Lemaître. In the 1920s, he'd been studying Albert Einstein's work, the equations dealing with the behavior of the universe as a whole. Einstein had concluded that the universe was static, unchanging, but Lemaître disagreed. He found that an expanding or contracting universe fit the equations better, and given the redshifts observed by Slipher, he proposed the universe itself was getting bigger, which is why the galaxies appeared to be moving away from us. Another brilliant physicist, Alexander Friedmann, had also reached the same conclusion. At the same time, astronomers were trying to determine the distances to the nebulae, now understood to be galaxies in their own right. As I mentioned in our first episode about galaxies, Edwin Hubble and his assistant Milton Humason were at the forefront of this. They observed variable stars in the Andromeda galaxy that allowed them to get the distance to the galaxy. They then observed some of the same galaxies Slipher did and measured their distances. When they compared distances to the redshift Slipher observed, they found that the farther away the galaxy was, the faster it was moving away from us. Let me repeat that because it's kind of important. The farther away a galaxy was, the faster it appeared to recede from us. Some other astronomers had also found similar results, but the work of Hubble and Humason clinched it. We now know it to be true for every distant galaxy we observe. They are all redshifted, all heading away from us. And this ties into what Lemaître had concluded. The universe is expanding. Wait, what? The universe is getting bigger? How can that be? What does that even mean? There are lots of different ways of looking at this. Lemaître himself suggested imagining the cosmic clock running backwards. Right now, as time inexorably marches on, all the galaxies in the sky are getting farther and farther away from us. But that means that in the past, they were closer together. Run the clock back far enough, and they get closer and closer together until at some point in the past, everything in the entire universe was crammed together into an uber-dense thing. That is a really, really weird thought. It's hard to imagine everything in the whole cosmos, every star, nebula, galaxy, every atom, electron, and proton, all squeezed together into one infinitely dense blob. But that's what the observations are telling us. Lemaître called this a primeval atom, or more colorfully, the cosmic egg. Fair enough, but this implications. If you squeeze all the energy everywhere into one place, that place is going to be hot. When the universe was a tiny dot, it would have been unimaginably, hellishly hot. Then, for some reason, it suddenly expanded violently and started cooling. This sounds an awful lot like an explosion. Bang! Involving the entire universe, which is big. What else would you call this, bud? The Big Bang. In fact, the term became popular when astronomer Fred Hoyle used it on a radio show and later in a widely read magazine article. Ironically, he meant it somewhat disparagingly since he didn't think the Big Bang model was correct. To his and many other astronomers' chagrin, the name stuck. I like it. It's not perfectly accurate, but it's succinct. Again, this is all pretty strange, and astronomers had a hard time accepting it. After all, it went against everything they thought was true at the time. In science, though, a hypothesis needs to make testable predictions before it can be taken seriously. What predictions could the Big Bang model of the universe make that we can observe today? The speed of light is fast, 300,000 kilometers per second, or about 1 billion kilometers per hour. Like I said, fast, but not infinitely fast. The sun is 150 million kilometers away. It takes light about 8 minutes to reach the Earth. So in a sense, you're seeing the sun as it was 8 minutes ago. The nearest star system to us is Alpha Centauri, 4.3 light years away. So we see it as it was 4.3 years ago. The Andromeda Galaxy is about 2.5 million light years away. The light we see from it now left that galaxy when Australopithecus walked the Earth. The farther away something is, the farther in the past we see it. This is called the look-back time, and it's a crucial tool for cosmology. By observing very distant objects, we can see the universe when it was young. You might think that we could see all the way back to the moment of the Big Bang, but there's a problem. At some point back in time, the universe was so hot and dense that it was the same temperature as the surface of a star. It would have been very luminous, but also opaque. As it expanded, it cooled and became transparent. If we look back far enough, that moment in time when it cleared up is as far back as we can see. What does that moment look like? By looking at the physics of the Big Bang, the math that describes how matter, energy, space, and time behave, astronomers could predict when this moment happened in the lifetime of the universe, a few 100,000 years after the bang itself. Using the idea of look-back time, they could predict how far away it would be from us and therefore calculate its redshift. Remember, redshift stretches the wavelength of light. The light the universe emitted at the time would have been like a star in the visible part of the electromagnetic spectrum. But the light that reaches us billions of years later, now, should be redshifted into microwave wavelengths. In 1965, a pair of radio astronomers announced they had found a signal in their radio telescope that was like a background noise coming from everywhere in the sky. They tried everything they could to explain it, including scraping out the bird poop inside their radio telescope in case that was causing it. But the only thing that made sense was that this was indeed the redshifted light from the early universe. They had discovered the glow of the fireball left over from the birth of the cosmos. Later, in the 1990s, satellite observations further refined the measurements of this cosmic microwave background, and now it's essentially confirmed. This glow was successfully predicted by the Big Bang model, and now we see it in exquisite detail. Its discovery was a huge step in cosmology. The redshift of distant galaxies and the cosmic background are not the only confirmations we have that the Big Bang model is correct. For example, the model also makes predictions about the elements we see in the universe. At first, when the universe was dense and hot, only subatomic particles could exist. But as the universe cooled, for a brief time, they could fuse and form heavier elements. The Big Bang model predicts certain abundances of elements, ratios of them compared to hydrogen, and that's just what we see in the universe. universe at large. Also, the sizes and shapes of the largest structures in the cosmos are in line with what a Big Bang model predicts. There's lots of other observational evidence as well. Pretty much every modern astronomer on Earth understands that the Big Bang model of how the universe got its start is the correct one. But what does it mean? I mean, physically, it's a very common misconception that the Big Bang was an explosion in space with everything rushing away from some point. But that's not what's really happening. Remember, I've talked about space being a thing in which matter and energy exist. Space can be warped or bent by mass, creating what we think of as gravity. When we talk about the universe expanding, we mean space itself is expanding. And when it does, it carries galaxies along with it. In a sense, it's like having a rubber ruler. When you pull on it, it gets longer, and the distance between the tick marks gets wider. When the ruler doubles in length, the tick marks that started out a millimeter apart are now 2 millimeters apart. But tick marks that were 10 centimeters apart are now 20 centimeters apart. In other words, the farther away a tick mark is, the faster it appears to move away. Sound familiar? That's just what galaxy redshifts are telling us. It also means that really the galaxies aren't actually doing any moving. It's that space between them is expanding. This may seem like a nitpicky semantic point, but it's physically true. The galaxies are, for all intents and purposes, standing still. The space in between them is where all the action is. And it gets even weirder. This is true no matter where you are in the universe. From any galaxy, it looks like all the others are rushing away from you. Look back at that ruler. No matter what tick mark you start with, when the ruler stretches from that spot, it looks like the tick marks are all moving away from you. This is what Einstein's equation showed and what Lemaître saw in them. Space is expanding. But that means the Big Bang wasn't an explosion in some pre-existing space. It was the initial exploding expansion of space itself. The universe isn't expanding into anything because it's all
We lost the sound.
Bart, are you there?
had a beginning.
Yeah,
and we
I'm
can
here.
see evidence of it. Not only that, but by measuring how
I'm just not
quickly it's
going on mute.
expanding, we can use math to run
Sorry.
the clock backwards.
Oh, when I
Okay,
went-
we lost the sound on the video.
The best measurement we have of the
Like,
age
that's
of
why
the
I can't
universe
go on mute.
is 13.82 billion
You
years.
can turn your microphone off rather than mute.
13.82 billion years. That's an amazing number. It's a long, long time, 3 times older than the Earth. But what gets me is that we can figure it out at all. Pretty smart, us apes. Today you learned that distant galaxies show a redshift in their spectrum, which means they're moving away from us. The universe is expanding. This means it used to be hot and dense, then it started expanding and cooling. This model of the universe's early behavior is called the Big Bang, and it was confirmed when the background radiation, the glow of the fireball, was detected in the 1960s. Other lines of evidence support it as well. Using this information, we have measured that the universe is nearly 14 billion years old. Crash Course Astronomy is produced in association with PBS Digital Studios. Head over to their YouTube channel to catch even more awesome videos. This episode was written by me, Phil Plake. The script was edited by Blake DiPastino, and our consultant is Dr. Michelle Fowler. It was directed by Nicholas Jenkins, edited by Nicole Sweeney. The sound designer is Michael Aranda, and the graphics team is Thought Cafe.
Okay. So that's the convention. So hold it. That is the conventional view of this for many people. Now, one of the things that he said in this was there's a mix of hydrogen, helium, and deuterium and lithium atoms that appeared. And those were measured, and the measurements matched what the theory showed. That's now been shown to be incorrect. Okay, the theory is in fact showing that there's something else going on that got missed somewhere. Furthermore, what I'm going to do now is just go to something that's fun, which is Hold on.
Before you do that,
Yeah,
let me make a suggestion to you.
go ahead.
There are two ways to mute in a Zoom meeting. One would be through the Zoom method that we all use for muting ourselves through the Zoom program. But independent, excuse me, independent of that, your computer has a little microphone button. Usually it's amongst the function keys at the very above the numbers. And one of them usually has a little image of a microphone.
Yeah, I see it.
If you use that when the video is playing, we won't hear the background noise. But when you mute it through Zoom, then we don't hear the video.
Got it. Okay, so I see the icon for the microphone. So I'll give that a try when I put this next thing on. But for right now, I'm actually going to be talking. So it's going to be hold on one sec. Okay. Can everybody see this? Let's
Yes.
see. Go into slideshow. Let's see. Now we got this same thing with this frame. Okay. Let me just go back to. Okay, I have no idea why this thing works this way. So we're going to go through two stories here, and I hope you'll find this fun. So the first one is the King James version of the Bible, and we'll go through Genesis 1. And then we're going to go through a short story written by the science fiction author Isaac Asimov called The Last Question. This was written in 1956 for a pulp magazine. And I think I actually saw it at my public library in 1959 or 1960 in a collection of short stories by Asimov. And I'm going to argue here that Asimov was really doing a better job than the King James version of the Bible in terms of Genesis. So you judge for yourself. We'll come back to this. So the first one is, in the beginning, God created the heavens and earth. The earth was without form and void, and darkness was over the face of the deep, and the Spirit of God was hovering over the face of the waters. And God said, "Let there be light," and there was light, and God saw that the light was good, and God separated the light from the darkness, and God called the light day, and the darkness he called night, and there was evening, and there was morning of the first day. So this is capturing that statement that we saw of in the primordial beginning, there was this gigantic nuclear fireball, and things had to cool down. And then when they did, then light could actually travel. So that was there, let there be light. And that created light from darkness. And so the King James Bible is so far doing fine. So now let's go to, what did Asimov do?
Just a quick question. What are the waters?
Well, that's left for I think that was a mistake in the translation, okay? I think there was, that is the start of Genesis, okay? So
Oh, yeah, I know. But I've always wondered what the waters
come
were.
from, you know? In fact, you don't even need the waters. You know, as you saw, the waters have nothing to do with it. So
Right.
it almost makes you wonder, like, did someone put this in? So now we're going to go to this last question. So this is taken out of Wikipedia. You can read the story. I'll send it out. I have it on an Acrobat file. So Asimov had fun writing the story. So the story centers around multivac, which is, you have to go back to when was this written? It was written in 1956. So at that point in time, computers were things that took up whole office buildings. Okay, they took up multiple floors of office buildings. They were these gigantic things. And so, here there's this story that starts with multivac, which is this humongous computer, which is designed to basically run planet Earth. And this all is in the year 2061, so it's 100 years out. And multivac is the protagonist in this thing. So there'll be 6 different scenes that Asimov runs through. I think there's 6 because Asimov did this for a pulp science fiction magazine, and they pay by the word. So Asimov was very good about putting a lot of words in these things to make sure he got enough money. So the people have just done the cutover of this incredible computer. They're about to have it take over running Earth and looking out toward pieces of the solar system. And someone there after the celebration says, well, why don't we ask how can the net amount of entropy in the universe be decreased? How can the universe is going to gradually get run down? Entropy will increase. All the heat will disappear. There'll be nothing but cold, and we'll be going to a state of maximum entropy, but it'll be 0 degrees Kelvin, absolute 0. And so the multivac is asked, how in the world do we reverse entropy? And multivac finally responds, there's insufficient data for a meaningful answer. So that's where we start. Now we go forward in time, and there's more and more later and greater different versions of multivac. He has, for example, one called microvac, which is even much, much more advanced, but is in fact much smaller than multivac. And they're running around out on some planet way out in the Milky Way galaxy. And they decide to ask microvac, how do we reverse entropy? And they said there's insufficient data for a meaningful answer. So then we go on and on through this. Finally, the entire universe, every planet of every star is just filled up with humanity. Asimov never had any aliens in any story. There were only robots and people, humans. And so in the very last scene, there's someone left there, and there's been trillions and trillions and trillions of human beings, and the stars are all flickering out, and the matter and energy is all dissipating, and the people that are there are asking multivac, which is now moved off into hyperspace, which is somewhere beyond gravity or time. How do I reverse entropy? And the automatic computer, or AC, isn't able to answer. And finally, the last person goes in and says, just keep working on it. So that now all of humanity is in hyperspace linked up with this automatic computer. And the AC keeps working on it and realizes that there is some things that got overlooked, and it does all kinds of calculations and so forth. And it finally discovers the answer, how to reverse entropy. But the problem is that there's no one left, since the universe is completely dead. So it decides to have a demonstration that'll fulfill the request of the last entity. And so the automatic computer said, let there be light, and there was light. Okay. So why in the world do I even think this is remotely possible? Why is this? Well, we have to go back to this little picture here and take a look at this. And I'm going to point out 2 things. One is we have matter over here in this 10-dimensional subspace, and we have dark matter. And the dark matter is immortal. There's only 2 states for dark matter. It's either active or it's asleep. It's somnolent. And those appear to be what are called spirits or souls. So they're there and they link with the body. So what Asimov was talking about of linking up into hyperspace is having your soul or spirit go off into this other space, and your body that's over here is going to decay. Now that's the first thing to keep in mind. The next thing is that we talked about the space-time that we live in has 4 dimensions. So there's 3 spatial dimensions called X, Y, and Z, and then there's time, but time is not a spatial dimension. It's not a measure of length. So we multiply it by the speed of light, which is meters per second. So that now meters per second times time gives us meters. So we have a length dimension here for our time dimension, but it's multiplied by the square root of -1. And the reason for this is the many measurements show if we try and compute distances in our space-time, they actually are a generalization of the Pythagorean theorem. So it's x squared plus y squared plus z squared plus ICT squared, and then you take the square root of that, and that gives you a distance in space-time. Well, if I square minus the square root of -1, I get a minus sign. So I get x squared plus y squared plus z squared minus ct, the quantity squared. And that's my unit of measure, okay? Now, if I go over here to this dark matter side of things, all of those dimensions are the same as the ones we're in, except they're multiplied by the square root of -1. I have no idea why this is. It's just what makes everything work out. So if I multiply everything by the square root of -1, then I have ix, iy, iz, and when I multiply I times I get -1. So here I have c multiplied by not time, but minus time. So in other words, over here in our dimensions, we seem to have positive time, and over here in these in these space-time, we have negative time. Okay, crazy that it is. This is where you have to just trust yourself that you're following this thing through. So there's 2 types of time: positive time and negative time is what's happening here. And over here, everything that started out here as humans and whatever that was linked to a soul, and they're all gone, and they're now all spirits, all souls, just like as Asimov said, they're all off here in this other subspace. Okay, now the other thing to keep in mind here is we have this information floating around, and the information is everywhere. It's in every compartment of space. It's in anything you could think of. It's there, and the information is sitting there and is playing games with the time going plus and minus. So what's going on? What Asimov is saying is that everything is decaying. Okay, all the matter is disappearing. There's even black holes, and the black holes are all evaporating. There's going to be nothing left there, and everything is going to be in dark matter, which again is not dark. It's just we can't see it. It's in this other subspace. So everything's over there, and it's controlling this information. So what it's doing is it's looking around and it says, you know, what I really want to do is come back and coalesce things. So it's going to take things that have all been spread out, and over some incredible interval, which is probably measured in trillions of years, the dark matter will control the information to go bring everything back to go collect together, and then it'll bounce. It'll bounce, and as we'll see, the nature of the bounce is that it'll start to create what we see around us, and in particular, it will start to create matter as well, which leads to what's going on. So the short of it is that there's the elements that Asimov was dealing with. He wrote the story as a joke, but it actually is probably more true than anyone realized. So let's go off. Let's get out of this. I think I'm done with this. Yeah, I am.
So a quick question. If
Yeah.
there's negative time and there's positive time
Yeah.
that would counterbalance each other, aren't we really talking about there just being a status or stasis? where everything is going on that we perceive, but it's really just stasis, that the universe is stasis.
Well, if you look at it this way, there's only dark matter. So now the time is this negative time. So everything is, you could conceptually think of it as running backwards, okay?
Right.
Except
So,
that,
so everything that's going on is actually not going on at the same time.
yeah, but there's really no notion of time, because if you think about it, what's there? The dark matter, again, I said there's two ways. It can either be active or asleep. Well, the only way it can be active is if it has some sort of energy source that it can couple to gravitationally. It needs some jostling, some heat to make it be active, okay? And that's why we have souls, is they're glad to be heated up and linked to us, okay? But in this scenario, they're all asleep because there's no heat left anywhere. It's all gone.
Okay.
They could still control, the scale. So we could conceptually think of what's going on here is a bounce where everything in a timeless interval, which if we actually looked at it and we're able to measure it, it's probably trillions of years, comes back and coalesces and bounces back out. And then we have this bang that occurred there as well.
Right.
So and the thing that I missed last year, and I apologize for this, was there's a huge amount of material now on this, and that's what we're going to be going through here now in some of these other things. So I'm just going to go to, hold on. What I'm going to be dealing with is there's a Nobel laureate, Roger Penrose, who's at Oxford, and he, in my opinion, he deserved the Nobel Prize in Physics. He's truly an amazing character. And so you can judge for yourself. He's this crusty Brit, and you'll see what's going on here. So here is Roger Penrose. And Roger Penrose will be talking about the Big Bang, and he'll be starting to say, well, there's this problem and that problem with it. And, remember, this guy is a professor of mathematics at Oxford. But he judge for yourself as you listen to him. He's trying to explain these concepts in very simple terms. So here we go.
Philosophers, theologians, physicists now begin to speculate on it. I really come to you because you have some very unique insights into the Big Bang.
But there's something almost paradoxical about this microwave background. It's telling us that there was something like the Big Bang there. But it's also telling us, because the observations of the microwave background, you can plot the frequency, plot the intensity against each frequency. You find this wonderful curve. It's the Planck curve, black body spectrum. And it agrees with that to an extraordinary precision, much better than you could produce in the lab. And this is telling us that the very early universe must have been in what's called thermal equilibrium. Now, thermal equilibrium, by definition, is the maximum random state. It's the state that the second law tells us we're going to get in the future. But there it is in the past. So why is it that the very special state that has to have been there at the beginning, otherwise we don't have a second law. The second law of thermodynamics tells us things get more and more random. Things get less and less random. So it must be very, very special. But what we find is that the matter, what we're seeing in this radiation is radiation as light, and that's being in equilibrium with matter. So that's what you're looking at, and that's at this maximum random state, maximum entropy state, we say. And something special about that was in the gravity. What you're not looking at is gravity. And the thing is that the universe was very, very uniform in the early days. And we think of uniform as being consistent with being random, if you like. But that's not true when gravity is the principal ingredient, because it tends to clump things together. The sun is out there, for instance, because it's clumped together out of a previously uniform distribution of of gas, and that sun gets hot. Background sky is cold, the sun is hot, and it's the difference between the hot sun and the cold sky that we live off, and that's where all life comes from. That. So that's the key thing. Now, so the universe was very special, but it was very special only in the gravity. Somehow gravity wasn't thermalized with everything else, and that's something which needs to be explained. To me, it's the greatest puzzle about the Big Bang. Now, I don't see most of these theories making any attempt to answer that question. Certainly the inflationary model doesn't. It only, in a certain sense, makes things worse. And the argument is that it smooths out the universe and things like this, but it doesn't do that unless you're already special, or even more special in the early stages. So if you follow the argument through, you see that it really doesn't explain this initial specialness. And it can't, because it's all consistent with the second law of thermodynamics, which says things get more and more random. So how could it have got more and more special in the early stages? There has to be something else. Now, for a long time, anybody that asked me what happened before the Big Bang, I would have given the conventional answer, which is Big Bang was this singular state where all our equations go haywire and time and space doesn't make any sense. Even the question before doesn't mean anything, you see. So that's the conventional answer. You say, you can't talk about it, it's just meaningless question.
There is no before.
There is no before. Another idea which I'm pursuing, which I think has a reasonable chance of being right. And this depends upon how you characterize the initial state of the universe. So what I'm saying is that the gravity is special. Everything else seems to have been as random as it could be. Now, can you characterize that in some geometrical way? Well, a colleague of mine, Paul Todd, who's at the Maths Institute here in Oxford, has had a particular way of characterizing this. I've worried about this for a long time. I formulated a thing I call the Weyl curvature hypothesis. Let's not worry about what that means. It's something about the particular type of space-time curvature that could have been present in the early universe. Now, my colleague Paul has a way of phrasing that in a nice geometrical way, which is to say that you could extend the universe to before the Big Bang. Now, this is just a mathematical statement. You're not saying you believe any physics here. You're saying this mathematical statement. You can extend it before to as long as you're somehow allowed to stretch the universe out. So I think, what's the best way of explaining this? I think there are some nice pictures that Escher has of a universe of angels and devils, and they're all within this circular boundary. And at the edge, you see, that's infinity. And the whole universe is squashed into this. Now, if you forget about the size of those angels and devils and just worry about shapes, then you can, doesn't matter how big they are, the little ones at the edge are the same sort of shape as the ones in the middle. But if you're prepared to stretch and squash in a uniform way, okay, then you could stretch that boundary out to infinity, or you could squash it back to this finite boundary. Now, there is a universe, and the universe in this picture stops at the edge, that's infinity. But you could imagine extending it to the other side and preserving this kind of geometry. It's called conformal geometry. That's a mathematical term, which means that, okay, you know about shapes, small shapes, but you don't know about sizes. So small and big count as the same, but different angles count as different. Different small shapes count as different. So if you don't mind stretching or squashing, then you can step outside this universe to another side to it. So I want you to imagine the same thing here. That you've got the Big Bang, which is somehow stretched out to be a surface, as though that's a one-time surface, but you could go before it. Now, this mathematical trick, I'm not saying this is real, I'm just saying it's a mathematical trick. This mathematical trick, if you phrase the condition on your universe in this way, you say you could extend to before, then that is a way of characterizing the initial state of the universe. The universe seems to be like that. It seems to be that the gravitational degrees of freedom are killed off, which is what this picture is expressing. It's hard to say this without being so technical, but I hope this sort of idea gets across. Okay, now that's one side of the picture, and if you like, the physical justification for this is that in the very early universe, the temperature was so high, the energies of particles were so high that it didn't matter a hoot what their masses were. See, mass is what you use if you want to build a clock. There's two fundamental equations in physics that I'm referring to here. One is the famous Planck law, which tells you energy equals E equals h nu. So the energy is proportional to frequency. The other is the famous, even more famous Einstein equation, E equals mc squared, which tells you that energy is proportional to mass. So if you put those two together, it says mass and frequency are basically the same thing. So that means that there's a clock, which is the frequency, is a measure of mass. Now, if you don't have any mass, or if mass becomes irrelevant, you can't build a clock. So in the early universe, the universe didn't know how to keep time. It lost track of how fast things were going. You see. And if you take that seriously, you can imagine going to before it. Now, it's a difficult idea to grasp, but it's mathematical. It makes mathematical sense. But it's hard to sort of think this is real physics, you see. But okay, that's one side. Now, the other side is think of a very remote future. What do we expect in the very remote?
We have the universe expanding.
The universe is expanding.
Without
And
limit.
it's accelerating its expansion, which is important for this whole picture. It wouldn't work otherwise. And this is this mysterious thing people worry about. They call it dark energy. Maybe it's just the Einstein's cosmological constant, which is the way I would look at it. But still, we don't know why it should be there, if you like. So, but in this picture, you need it. So I want to say, what's the remote future in this picture? Well, the universe expands, it exponentially expands. And okay, there's black holes lying around, which have got lots of mass in them. According to Stephen Hawking, these things will, in a very remote future, the universe will cool down to lower than the temperature of any given black hole, even huge ones which have a very low temperature. Even huge ones which have a very low temperature, and they will evaporate away, get smaller and smaller and smaller, and eventually go off with a pop. That's the picture. Now I'm accepting that. I think that's probably right, although there's some conjectural aspects to this. And eventually, all the matter in the universe will disappear apart from radiation. Now,
Very dispersed.
That's right. There's certain assumptions which go into this, but let's accept that. There's nothing left but radiation, very dispersed. Now, how do you talk about the very remote future? In fact, the picture I'm trying to describe is a sort of result of my worrying about how boring the universe is. You see, it's going to get pretty boring, you see. And I can't think of anything more boring than waiting around for a black hole finally to disappear pop. It sounds incredibly boring. But then I thought, well, who's there to be bored? Not us, you see. The only things around will be these photons and things, and it's pretty hard to bore a photon. A photon doesn't experience any passage of time. So eternity is no big deal to a photon. Just, whoop, there it is, you see. And there's a sort of mathematical trick, another mathematical trick, which I've certainly been involved with for a long time. How do you talk about infinity in relativity, in Einstein's theory, in Einstein's general relativity? How do you talk about infinity? Well, you'd use the same conformal trick. But now, instead of stretching out, which is what I did for the Big Bang before, I'm squashing it down. So I'm saying that in the remote future, there's nothing left which has any mass, if that's the case. Somehow the universe doesn't know how to keep time in the remote future, doesn't know how big it is, you see. So the universe forgets how big it is, it says. And it might as well be a small new universe. So the picture, okay, it's crazy.
I followed everything until that very last step where we have a complete expansion, we have complete dispersion, no mass, photon radiations, and the similarity was that there's no clock. Because you have no mass, and that's the same characteristic of the early universe when it was very small. But you have this very big
That's right.
universe that has no clock. And now, how do you get to that small universe that has no clock?
But the point is that it doesn't know the difference between big and small.
Because it has no clock.
It has no clock. You see, okay, you've got the speed of light, which enables you to transform from time to space.
Yeah.
But since it's got no clocks, it has no way of measuring distance either. So spatial distance becomes irrelevant. Temporal distance becomes irrelevant, or time.
So the universe forgets how big it is.
It forgets how big it is. So it sort of lost track of that, and it becomes the next Big Bang. Now, of course, this needs to be filled out with some honest mathematics, and it also needs to be related to observation. And the thing is, you might think it's hopeless. How would you ever know whether there was a previous universe, you see? But it's not so hopeless. And the first point is that I mentioned inflation. Inflationary universe is that in the early stages, there was this exponential expansion. But in this model, the exponential expansion took place in the very remote future. And that is quite consistent with our present day view. The universe will expand exponentially. And so you will get same features that you get with inflation, but without inflation. And so then the idea is that that exponentially expanding universe forgets how big it is, and it becomes the Big Bang of the next scale. Now, how do you observe? I mean, as I say, can you do observation apart from agreeing with there are these things called scale invariance, which is one of the observational supports for inflation. So I'm saying that will, I think, will carry over to this particular model. Now, the other thing is that there will actually be a little bit of disturbances which will come about from, I'll say there'll be in the remote future lots of black holes before they finally disappear with pops. They'll be around for a long time. And in the process, okay, in the middle of galaxies, our own galaxy, for instance, has a black hole in the middle of it of something like 3 million times the mass of the sun. Okay, that's quite sort of usual for a galaxy. In galaxies and clusters will run into each other, the black holes will spiral around each other, swallow each other up. In that process, they will emit gravitational waves, ripples in space-time, a sort of gravitational analog of light. These ripples will make their mark on infinity. It's a bit hard to explain that one too. But although they get infinitely dispersed, they still, because you have to squash it down again to see what's going on, it's still there. And they will have an influence on the next stage of the universe. And so in principle, it will require a delicate piece of analysis. You should be able to see that, if I can use an analogy here, think of a pond, and it rains on the pond. Every time a drop of water hits the pond, a ripple comes out. Now that's like these black holes colliding, and a ripple goes out of disturbance of gravitational waves. So you get these ripples. After a while, the rain stops. That's when the black holes have all disappeared. See, after a while, the rain stops, but you still see the ripples all messy. It looks like just a mess, you see. But in principle, you should be able to work out that these ripples are made up out of individual places where the raindrops have hit. In the same way, I'd say you could look at this background radiation, and there's now a lot of information from these new satellites and so on, which have been observing the very detailed structure of this background radiation. You should be able to analyze it and see whether it's made up out of these individual events which are spread out in this way. Now that's something for the future. Well, it could completely destroy the whole idea. On the other hand, it might turn out that this is an
I
observation.
find it absolutely fascinating that it's even possible to consider what happened before the Big Bang.
Well, it's not so outrageous. Okay, it is outrageous, but not so. It's conceivable that this would work. Yeah, and it does explain the very special nature of the Big Bang, because the whole thing doesn't work without that. So that's I think one positive feature that other theories don't seem to give us.
Okay, so there's a lot of stuff there. I'm going to just do one thing. I'm gonna go to, he mentioned angels and devils, which is this, angels and demons, which is this,
I just saw it in person in Houston.
you did?
Yeah, I was in Houston with the kids for robotics, and we went to the Museum of Fine Arts of Houston, and they had a huge Escher exhibit, some 500 of his work. It was totally amazing.
Okay. So I'm just gonna go here to, am I still in the screen share? I thought I got out of it.
You're out of it.
Hold on. Go here. Where did the share go? Just a sec. Oh, here it is. Too many screens. So this is just a short animation to show you angels and devils. And look at out on the edge, and you'll see that's what he was talking about. There's no sound to this. So see how many are appearing on the edge? And then they turn into demons. The angels all flip into demons. And there you have it. Okay, so he raised a number of points. One was, observing this stuff. Now, what's interesting, we're going to go through what Ron Cowan did. We're not going to do it this time. We'll do it next time. But Ron actually carried out a whole bunch of observations on this, which we'll go through. And they suggest that there really is a big bounce. And there's been multiple of these big bounces that have occurred. And we're just in one of them. I went and looked on the web, and there's a number of things by the, I'll just say, Vedic school, where they claim that we're in the 29th bounce, and we have many more to go. I have no idea where that number comes from, why we're in number 29. But the thing is that there's just constant destruction and creation and destruction that's occurring here, is the takeaway from the modern cosmology. And what Ron observed will put a lot of meat on the bones. And you can judge for yourself, of course. This is, really, it suggests, what is the point of it all? If the point of it all is to go through these cycles, I mean, what are we doing? But that's another question that I'll just leave for you. Now, since I'm doing all this from this place, why don't we just call it a night, a short one tonight, and I'll send out the recording. I'll send out the Isaac Asimov's short story, so you can all read the short story, and the slide decks that you saw there, so you'll see what's going on. And next time we'll go into more of these videos and more of what Ron observed. And again, I apologize for the internet mess up. I hope the noise wasn't too objectionable, but it's trying not inconvenience people. There again are a bunch of videos on the website, so you can go there and look at more of these if you wish. But we'll be covering several of them next time, as well as what Ron did, and this will give you the bigger picture of the big bounce and why this is driving everything. So
It was all perfect. Thank you very much.
well, thank you for putting up with this. It's never a dull
Yeah,
moment.
pretty awesome.
Yeah, McDonald's next time.
I know. Whoever has Wi-Fi, Dunkin' Donuts is closest. So,
Thanks, Bart.
okay.
Thank you.
Okay, watch
Thank
it.
you.
Bye-bye.
Bye-bye.
Good weekend.
Yeah, you too. Enjoy the weather.